So far we've seen that reactions have different rates, and how would you predict what kind of a rate different reactions would have? What factors would affect that? The first one is the nature of the reactants, physical state, for example. Reactants, say solid reactants aren't going to react as quickly because the atoms don't have as much contact with each other. Their chemical nature, some chemicals are more reactive than others. Temperature plays a big role, so typically if you increase the temperature, you'll increase the reaction rate. Catalysis, we will get to in a few videos. That is where you have something that you add to a reaction that's not used up, that speeds it up. And reactant concentration, so typically the higher the concentration, the faster the reaction. A way to numerically represent how fast a reaction will go based on concentrations is the rate law. It's the relationship between the rate of the reaction and the concentration of the reactants. Now, this is extremely important, and people forget it. The rate law must be determined experimentally. You cannot look at a balanced equation and know what the rate law is. You need to look at data to determine it. The rate of a reaction is going to be directly proportional to the concentration of each reactant raised to a power. So rate laws are going to look like this. For our generic reaction, some A plus some B goes to products. The rate law would have this form. The rate is going to be K, lowercase k, which is the rate constant, times the concentration of A to some power, times the concentration of B to some power. There we can then plug in any concentrations for A and B, as long as you know the rate constant and the rate and the orders of the reaction, those exponents, you will be able to determine the rate of the reaction. So reaction order, let's talk about those exponents. They're called the order of the reaction. And if you add the exponents up, that will give you the overall order of the reaction. So the this reaction here, the rate is the rate constant times nitrous oxide squared times oxygen, and it's second order with respect to NO. First order with respect to O2, there's a 1 there that's assumed, and third order overall, because 2 plus 1 equals 3. So you can give the order with respect to each individual reactant, and then the overall order of the reaction is the exponents added together. So we can see what different reactions look like versus time. If a reaction with respect to a particular reactant is zero order, it's not dependent on the concentration of that reactant, and so there you get just a straight line. If it's first order, you get kind of a curve like that. Second order, a curve like that. Then we can do the rate versus, this was the concentration versus time. This is the rate versus the concentration. So a zero order, not dependent on concentration, your rate stays steady no matter what the concentration is. First order, it's going to depend linearly. Second order, it's going to be a quadratic equation if you plot that rate versus the concentration of the reactant. Here are some sample rate laws. It can be just first order with respect to the only reactant. On occasion, you'll get fractions. That is rare. In this class, you're looking for rates of 0, 1, or 2. Orders of the reaction of 0, 1, or 2. Here we have one. You can see you have some coefficients. The coefficient has nothing to do at all with what the order of the reaction is. And then the bottom one is called autocatalytic. because the presence of a product is affecting the rate. So let's work through an example. The rate equation for the reaction of NO with ozone is K times NO times O3. If the rate is 6.6 times 10 to the minus 5th molar per second, when NO is 1 times 10 to the negative 6 molar and O3 is 3 times 10 to the minus 6 molar, calculate the rate constant. So here we have rate is equal to lowercase k times NO times O3, and we can just plug numbers in here. So our rate is 6.60 times 10 to the minus 5 molarity per second is equal to our lowercase k times 1 times 10 to the minus 6th molar times 3 times 10 to the minus 6th molar. Then I can solve for my k, and I get 2.20 times 10 to the minus 7. Then this needs units on it. So my units over here are molarity per second. My units over here are molarity times molarity. And so I'm going to need my units on my k to have a per second on the bottom and a also a molarity on the bottom, so that when I take 1 over molarity times seconds times molarity, I end up with units of m over s, which is the same as on that side. So my units here are, so you can either write it as 1 over m times s or m to the minus 1 second to the minus 1. They're the same thing. Let's dig in a little bit more to these orders of reaction. If a reaction is zero order, the rate is always the same. Doubling your concentration isn't going to have an effect. If your reaction is first order, your rate is directly proportional to the reactant concentration. So if you double your concentration of A, you're going to double the rate of the reaction. If a reaction is second order, if you double the concentration, your rate is going to quadruple because it will square the reactant concentration. And so we can set up an experiment where we change the concentration of each reactant individually by doubling it, and then see what happens to our rate. If it does nothing, it's zero order. If it doubles, it's first order. If it quadruples, it's second order. And here's the graphical representation of what I just talked about. We saw this slide earlier, our different rates. Okay, when there are multiple reactants, if you change any of the reactants, you're going to change the overall rate. So what you should do is change the initial concentration of one reactant at a time, focusing on one variable, and then you can look at the effect of that reactant's concentration on the overall rate. So let's work through a problem here. Determine the rate law and rate constant for the reaction given here, given the data below. So here's our data table. And if you compare the two experiments in blue, experiment 1 and experiment 2, you'll notice that your concentration of NO2 doubles, but your concentration of carbon monoxide stays the same. So if you compare those two, you can find what the N value here is, what the order of the reaction with respect to nitrogen dioxide is. So if we doubled our reactant concentration, our reaction rate here quadrupled. went from 0.21 to, or 0.0021 to 0.0082. If we actually do the math, you can see that our concentration doubled. If we divide the rates the same way, we get an answer of about 4, so it quadrupled. So our rate of the reaction with respect to nitrogen dioxide is 2. Then we can repeat that for the other reactants. So here, if we compare experiments 2 and 3 now, our nitrogen dioxide stayed the same, but our carbon monoxide doubled. What happened to our rate? It stayed the same, nothing happened, which means our reaction is 0 order with regards to carbon monoxide. When we doubled our concentration, the rate did not change, so our reaction is 0 order with respect to carbon monoxide. So now we've solved the first part. We know that our rate is our rate constant times nitrogen dioxide squared times carbon monoxide to the 0 power, which cancels that out. So overall, here is our rate. Then, that's not all the question asked. It also asked for the rate constant. You can find the rate constant by plugging in any of the values. So you know the initial rate and concentration for several different concentrations. If you were doing this in a lab, you would calculate the rate constant from all of the experiments and average them together. So here we're just doing it for experiment 1. We have our rate that we plugged in. We're solving for a K value. We have our initial concentration that we're squaring. This one doesn't matter, didn't affect the rate, so we don't have to put anything in there. If we do our math, we can find that K is 0.21 per molar per second. So here's a practice one that's very similar to the previous one. Go ahead and pause the video and work it through, and then I will work it through as well. All right, so for our NH4 plus, we can look at experiments 1 and 2. So our concentration, we'll do experiment 2 divided by experiment 1, so that's going to be 0.06000200 gets us 3, and then 32.3 divided by 10.8 gets us 2.99, which is essentially 3. So let's see, my rate is equal to K times my concentration of NH4 plus to some power. Here we found that when we tripled our concentration, we tripled our rate, which means we're first order with regards to NH4 plus. And then we have our NO2 minus. Let's compare 3 and 4. So this is going to be 4 over 3. So 0.0404 divided by 0.0202 gets me approximately 2. And 21.6 divided by 10.8 is going to get me also about 2. So we are also first order with respect to NO2 minus. Then it also wants to know the rate constant, so we can plug in data from any of these. So my rate, let's just do experiment 1. So 10.8 times 10 to the minus 7 is equal to my K times 0.02 to the first power times 0.2 to the first power. And then I can solve for my K. I get an answer of 2.7 times 10 to the minus 4, and my units on this K are also going to be per molar per second.